And then we apply this principle to design a heat exchanger system to optimize its effectiveness for heat transfer. And I will show you, there is another paper on this, so you can get a lot of detail from there. So here, we are actually using we designed the whole heat exchanger. It's an industrial system with a digital twin written in Simulink, and we used factorial design method, that was this optimal matrix. And you can see here that this is the heat exchanger effectiveness changes over time. And this is important. I'm going as fast as we can. In this particular design problem, we have identified that self-control complexity level is the most impactful, and that needs to be controlled for the design. And we designed a new heat exchanger system based on the complexity, where we try to reduce complexity but increase effectiveness of heat transfer. And that was our goal. One important parameter in all of this, stopping criteria. When you are doing this optimization, you need to understand when to stop optimizing. Self-engineering is good, but it's not possible to self-engineer forever. So when to stop? And actually there is loss every time you repeat. And we have seen that in simulation. So here the threshold was 50% of the maximum effectiveness we achieved. As soon as we reach that, we stop. But that part is done through simulation. It's a long kind of experiment we are doing. Then we started looking deeper into biological systems. But can we learn more from biology on self-cleaning, self-adjusting, self-repairing areas? And we studied 8 different biological systems. And this study is continuing. And I'm really thrilled by some of the biological problems, biological behavior, which is still very difficult to emulate. Many properties you can emulate in engineering systems, but the way, the ease of creating cells, new material in biology, in our bodies, not much work is going on now, artificially replicating that in engineering systems. That's still more work necessary. And then we looked at complexity analysis of these with 23 students and 9 experts, and we looked at normalized mean for redundancy versus self-control. You can see here, self-control again came out as one of the important factors for these biological systems. We try to form some design rules which will help people. So my ultimate goal in all of this is to guide design of new machines, which can operate either self-repair or self-adjust or self-adapt with changing circumstances. And we create some rules for that. So I want to highlight as a final point, replication of biological mechanism of repair and maintenance in engineering product needs further research. And what is important in all of this, when we do repair, how do we measure the quality of the repair itself? That's actually very, very challenging if you are trying to do that in situ as the changes are happening. You should not be stopping until the quality of the repair is right. And there are significant implications of this in life-threatening applications. For example, in aerospace, if you say I'm repairing the aerostructures or aero profile of an aircraft in situ as it flies, And you cannot guarantee the quality. It's not acceptable. It's not going to pass any certification, right? So quality and assurance of quality in this particular case is very important. Thank you.
Wonderful talk and dreaming about the self-cleaning house.
Thank you.
We would like to attend a couple of questions. Are there any questions for Dr. Roy?
Yes, ma'am.
I heard the most important thing nowadays is know how to ask good questions, right, in the AI era.
Thank you, sir, for your talk, and I'm very happy that today I got the opportunity to how we have integrated biology in the technology. So it's a very different kind of new experience, but I'm really surprised because biology has some blessings of nature and different biologies. Different people have a different biology. Some cancer patients that cured after the radiation therapy or chemotherapy, and some, despite all kinds of very costly treatment, died. But as this self-engineering, there is a repeatability, redundancy, and the self-control. So I think it is totally based on the predictions, as the predictions made by us, and we have integrated the systems. But somewhere, I think the systems will not be able to repair themselves, because every kind, the problem will be the different for the different mechanisms. Sometimes there is a high voltage power, or sometimes there is a low voltage short circuit. So this self-engineering or this can be really make some develop some kind of devices or equipments, or we have it is totally prediction based, or there are or we develop some kind of mechanism to manufacture some or develop some kind of devices, or there is a AI based system that the system should be so intelligent that can control that machine. Or I would like some favor that if you know some kind of devices, you are working on that, please name some devices. Because somewhere I think that this will not be feasible or totally give the correct results.
Thank you. I think it's a very good question. Let me give you some examples. For materials, there is self-healing material already available. For example, in construction, in turbine blades, coatings of turbine blades. Today, there are research groups who have developed material which, if crack is generated with environmental closeness, that means temperature as well as access to oxygen, it bursts and it closes the gap in the cracks. That is already in robotics. We have self-adaptive robotics already. A number of groups around the world is doing research. Quite a bit of references are published in those terms, of these terms. So there are examples which are already working, but none of them are commercially possible yet. And that's something we should be doing.
Thanks for your talk. Actually, during your talk, what I have observed that intuitive AI, or you can say that partially generative AI has been shifted from generative AI to prompt AI to point AI. Right now, most of the booming sectors that are basically going to be based upon the technology like decision making kind of thing, in which most of the things that are going to happen in the health sector only. So what I am supposing that if human computer interaction, that was basically the focus of this, whatever the emerging technologies were there, right now is converging towards the brain-computer mapping. These kind of stimulations or these kind of simulations are pretty complex. So assisting these kind of human-computer interaction to the brain-computer interfacing or the mapping, how the people should get inside and how the exploration of these kind of things should happen in the future.
Okay, so first of all, I need to clarify. My work is in big engineering machines, okay, which has long life, like aircraft, automotive. So I'm not an expert in medical devices, and so that's important for me to qualify. But I can give you my perspective, how this could be used. I think, first of all, equivalence of that in life-saving equipment in medical application would be, I would say, avoiding failures when in operation or gracious failure when in operation, so that machines doesn't break as it is treating patients. That could be one aspect we could look at through this kind of analysis. So that's probably the closest.
Thank you, Dr. Roy.
Thank you. Thank you very much.
Okay, next we have IBM India. Title of the talk is The Era of Quantum Utility and Beyond. Sounds very, very cutting edge. Okay, let's welcome Dr. L. Ventakar Subramanian. Let's first welcome him with the
Morning. Can you hear me at the back? No? Are you able to does this work? Hello, good morning. Can you hear me now? Yes, sir. Okay, so it's a pleasure to be here. So how many people here have used a quantum computer? Okay, so my focus is going to be at that back end there. Okay, all of you have to use a quantum computer at the end of this day, today. Okay, so all of you, I'll tell you how you can use a quantum computer, and you are going to go and create an account today and start using a quantum computer. Okay? So for the first time in history, computing has branched. There are now, well, okay, we also heard about a DNA computer. So, among digital computers, there are two kinds of computers now. One is your computer, your laptop, your mobile phone, which uses bits as the fundamental unit of computation. Bits, zeros and ones. So all the computers today, like your mobile phone, laptop, supercomputer, all of them have bits as the unit of computation. Now for the first time in history, there is a new kind of computer called the quantum computer, which does not use bits. Okay. So what does it use? Yes, it uses what is called a qubit, quantum bit. And what is special about a quantum bit? The quantum bit can be 0 and 1 and simultaneously. So it can take on values between 0 and 1, including 0 and 1, everything else in between also. Which means that it is now able to do much bigger computations using the same unit. Okay, so that's what the quantum computer is about. So why is this quantum computer special? How do I change? So today when you write a computer program, let's say you use a language like, what is the most popular language everyone uses? Python? Java. Okay, Java. So you write a code in Java, then what happens? How does it run on the computer? There is something called compilation. What is a compiler?
Translator.
Yes, it translates your Java code, which is written in higher level language, into machine language. And machine language is? Yes, a string of zeros and ones, which runs on your computer. On a quantum computer, again, you use a higher level language, like Java, like C, like Python. The same languages you can use for programming a quantum computer also. But now the compiler doesn't convert it into a string of zeros and ones. What does it do? Okay, we'll figure that out. So this used to be the most powerful supercomputer in the world. Everyone here knows Moore's law?
No.
What is Moore's law? Moore's law, who knows at the back? It says that compute power doubles every 18 months. So you have a mobile phone today, which you bought today. After 18 months, what will happen? You'll have a mobile phone which is double this power. That's why all of us want to buy new mobile phones. Better camera, more games, more storage, more faster processing. So all of that is because of Moore's law, right? Moore's law has been active for the past several decades. But in spite of Moore's law, there are problems which supercomputers cannot solve. A simple problem. We were talking a lot about biology right now, right? So take the example of caffeine. Caffeine is a small molecule. If you wanted to model caffeine on a computer, today's best supercomputer, it's not possible. Why? Because modeling caffeine takes 10 to the power 48 bits. Do we have a supercomputer that big? We don't have. Are we ever going to build one that big? That's equal to 10% of the number of atoms on Earth. Are we ever going to build a supercomputer that big? Very unlikely, right? And that's where the quantum computer comes in. Instead of requiring 10 to the power 48 bits to model caffeine, all you require are 160 qubits. Why is modeling a molecule important? Anybody know how medicines are made? So, in our body, there are at least 25,000 proteins. Proteins are three-dimensional objects like this. One protein is like this, another protein is like this, another protein is like this. So there are multiple shapes of proteins. Now, what is disease? A protein like this becomes like this. That's disease. What is medicine? Medicine is a thing which comes. That's medicine. Okay. So finding medicines is a big challenge because for every disease you want to fix it. The protein that has been affected, you want to fix it. You know about coronavirus?
Yes, sir.
What is the shape of coronavirus? Like this with spikes. And what happened? In the lungs there was a beautiful receptor for the coronavirus, like this. Coronavirus comes, tick, fits. Okay, that's what happened. So what is medicine for coronavirus? Something which blocks. Instead of, it blocks that. It doesn't allow you to come, coronavirus to come and fit into this. Okay. So finding medicines. To find medicines, you need to be able to model the molecules. Okay. That's what you have to do. Okay, you find a medicine, then what happens is today, you take that medicine to AIIMS. You take 25 people with disease, 25 without, and then you figure out how is the medicine acting on them. Who knows about side effects? What is side effects? When a medicine which is made to correct this also goes and fits other proteins which are in your body, that is called side effects. Today we are not able to predict side effects because we are not able to model molecular interactions using our best supercomputers also. And that's why quantum computers come in, where they are able to do this modeling on a molecular stage. But why are quantum computers good at doing this modeling? So quantum computers are good at modeling because they don't use bits and they use what are called qubits. And qubits, as I said, have this property that not only can they take on 0 and 1, but they can take on all the intermediate states also. And because of that, quantum computers are able to model things like molecules, medicines, new materials, all of these things much better than your classical computers can. And that's the reason why quantum computers, today there are 34 countries which have national quantum missions. Why? Because they all believe that whoever takes the lead in quantum computing will have several decades of economic dominance over Earth. That's the reason why every country is now having a national quantum mission of their own, and they're encouraging young people like you to go and start using quantum computers, to start programming them so that you are able to solve problems which today we cannot solve. What are those problems? Medicine. Today it takes 10 years to make one medicine. Climate change. We don't know how to model the earth. We don't know how to model many of the things today. Another example. So how many people here have used ChatGPT? Who doesn't use ChatGPT here? Anybody who is not using ChatGPT? Oh, ma'am is here. Okay, good. So ma'am doesn't use ChatGPT, but ChatGPT is something which is now brought AI to our desktops. Okay, that's what has happened. It has enabled each one of us to the power of, writing, the power of being able to answer questions about which, something like an assistant, you have an assistant for yourself. But in the workplace, what has happened is, for example, HR, that function, human resources, today it doesn't exist in many offices. They've been replaced by HR GPT. Things like marketing, replaced by marketing GPT. Even programming. Many of you, I know, might be learning programming and stuff. But in my office, I see that something which used to take me 7 days to, or 10 days to do, now I can do it in 2 days. Why? Because I can now use these co-pilots which do the coding for me. I don't have to sit and write code anymore. So these things are able to help me in writing code. But AI has a big problem. How does AI work? Anybody at the back? Okay, when you were a child, how did you learn to identify a cat? Your mother or father showed you cat, and then you said, next time a cat comes, you said cat. How many cats did you have to see? 30? 50? How many? 1, 2, 30, 50, 100? 1. So most humans just require one cat before they can identify another cat. Okay. Do you know how many cats AI has to see? Yeah, somebody said 1,000. It's more than 1,000. You need to show it cat from this angle, cat like this, with occluded cat, kali billi, brown billi, all kinds of billies before it recognizes cat. So AI has a big problem today, that it is not very efficient. Our brain is able to identify cat after one cat. Why? Because we have a very efficient representation, and that's what the biology computers are also trying to do, right? They're trying to take that very efficient way of representing data in our brain, which the computer today is not able to do. The computer is good, it does a lot of AI, very nice, but it's not able to. This cat problem persists today, which is that it needs thousands of cats before it recognizes one cat. And that's because the data representation inside the computer, because of the binary representation, number one, because of the way it stores it, retrieves it, the way it builds that mathematical model, it's very complicated. And that's what the quantum computer is trying to simplify. Okay, it's trying to get closer to the human representation, where human requires one, AI today requires thousands. Quantum computing is trying to bring a mathematical representation space which brings it closer to the human way of representing the data and doing the computations on top of it. So yes, it doesn't need one, but a few tens we are seeing are sufficient for AI. So because of that, we know that quantum computing, the challenge is to better represent the data, to bring the data to a much more easier form for us to manipulate and understand the nature around us. So I talked about HR GPT, all the other GPTs which are coming up. Because of the Billy problem, today every time one GPT comes up, what happens on the other side? One power station comes up. So by the year 2027, Earth will be filled with power stations. If we build all these LLMs using current AI. And hence AI has to improve. It has to solve the Billy problem which I just told you, which is requiring lot of data to represent simple models, which we are not able to do today, right? So with that, I told you today, you have to use a quantum computer before the end of the day, just like you use Google. Please go and type on Google, just type IBM Quantum. It will take you to a place where you can open an account on a quantum computer. Okay. On a quantum computer, you can open an account and use that to program a quantum computer. Just do hello world using a quantum computer, so that tomorrow when you come here you can say that I have used a quantum computer. Okay, so please do that. In the world today, India is the place where maximum number of quantum software engineers are there. So please join them. Today India is the talent hub for quantum computing. Okay, and it's because of young people like you. So please go and start using it. So thank you so much. I'll stop.
Thank you. I think we're gonna catch up with the time. So let's show our token of appreciation for this wonderful talk of our new era in quantum computing with the IBM quantum experience. I would like to take a couple of questions. Are there any questions? Okay, so I'll just briefly ask a couple of questions. So, any other questions? Okay, so now we're going to have this error issue. So how does IBM plan to deal with it? And then how long can we have some kind of expectation that it's going to do the coffee?
Yeah. So, ma'am asked this very important question. So today, the quantum computers have error in it. So which means that, for example, your bit, if you place it in 0 or 1, let's say you place it in 0, it remains in 0 forever. But on a quantum computer, you place it in one of the states, let's say 0 or any other state, it is going to remain there only for a few milliseconds. Okay, that's it, milliseconds. And lost. After that, it's gone. Okay. So, error correction right now, according to the roadmap that IBM has, will happen in the year 2029. 2029, 4 years from now. But does that mean quantum computers are useless before that? No. Even our classical computers, error correction came in 1950, 51, 52. But even before that, they were used in World War for decrypting, breaking codes and stuff, right? So quantum computers, they are expected to become useful in the next 1 or 2 years before error correction. Right now, they are using what is called error mitigation. Okay, so error mitigation is what is being used. And the important question of when is the coffee molecule going to get modeled? So in the next 2 to 3 years, that's going to happen. Okay, so already people have started modeling some of the small molecules using the existing quantum computers.
Thank you. So the next important question is, we want to use IBM Quantum, and we know that there's some limited number of qubits for a regular user. And how can we get hold of the larger qubits? Who do we contact, right? How do we get it?
Yeah, sure. So actually, IBM Quantum, I told you can go and start accessing the quantum computer today. Okay. So you can use the 127 and 156 qubits today. Everyone can. But the free user is limited to 10 minutes a month. 10 minutes a month. is what anybody can use, okay? But that's a beautiful way to get started. You can get started using the 10 free minutes. But beyond that, if you want to use the paid access, which in India, IIT Madras has, LTI Mindtree, there are a few entities in India which already have this access to unlimited quantum computer because they pay for it. So if you want paid access, you can contact me or anybody in IBM and they will figure it out.
Thank you so much. Of course, we know that quantum is probably going to solve our problem on the system costs and space and also energy. So we look into the quantum era in a few years, right? Thank you so much, and we're going to welcome the next speaker. It's going to be Dr. Puni Kumar. As from Lucknow University, Lucknow, India. And the title is The Quantum Revolution, a Centennial Journey. That's really exciting. So we have another quantum talk. We have a lot of quantum talk. Thank you so much. First is welcome Professor with the flower.
I am a physicist by profession and I am a student of physics. So I will be talking about quantum from a physics point of view, how the concept of quantum came into being, what were the roots, and I will make you think in the last that what is quantum technology and are the technologies available really quantum, in what way they are quantum, and the concept of quantum is not new, it is a centuries old concept, and we are celebrating a century of of the modern concept of quantum, like Max Planck gave it just 100 years back in 1924. So, I am from University of Lucknow. This is my department. This is a 150-year-old building, and we are the oldest university in this province. This is my lab, this is my workplace. This is my team. We work on quantum plasmas. So, a brief outline of what I will be talking. Why the quantum concept came into being, why it was needed, why the classical concepts failed, and who were the pioneers of the quantum concept, and in what sense it influenced the technology in the early 50s or 60s. And that was the first quantum revolution. And after that, we came to the second quantum revolution, and now we are in the midst of the second and the third quantum revolution. Whatever talks we have just gone through, some were of the second quantum revolution and one was of the third quantum revolution. So we are in the middle of that. And in the last I will be coming towards what that I am doing in quantum. So as far as classical concept is concerned, we were concerned about mass, but we were not concerned about particle. There are two sides. This is mass, this is particle. So in classical concepts, when you start learning physics, you thought about Newtonian physics. It was only this mass. But it was a macroscopic concept. It could not explain the energy quantization, the light-matter interaction, and the atomic stability. So there were some puzzles remained answered, like the radiation emitted by the black body. Theoretically, what we predict that as soon as the wavelength decreases, the energy will go infinite into a mathematical singularity. But practically, what we observed that it was not going this way; it was going some other way. So this was called ultraviolet catastrophe. The second problem was the photoelectric effect. The basic concept was then when photons are incident on the metal surface, electrons will come out. As a person who is studying only classical concepts, he will say that this emission will start as soon as the photons will come, but practically it was not happening. And simply a light coming from any of the atomic sources, what I would expect, a big periodic spectrum should be continuous like this kind of thing, but practically it was a discrete spectrum. So the story started with Max Planck. He's from Kiel University, Germany, and he came up with a concept that energy is in terms of a quantum of bundles, and we can define it as a product of a constant into the frequency of the radiation. And last year I happened to be with the descendants of the group, and this is a photograph. He was the person who changed the course of sciences. Like we are talking of quantum technology and quantum physics, so he was the person who gave the modern quantum theory. Next came Albert Einstein, who said that there is a minimum threshold energy required for the electron to be emitted from the metal surface. Then came Niels Bohr, who gave the quantum model regarding the absorption of the photon and the emission of an electron from the orbit. Then came Heisenberg, who gave a matrix method and in terms of uncertainties. This uncertainty is very important for quantum computers. Quantum computers is based on this concept only. We will discuss it later on. And then came Schrödinger, who gave the wave nature, how the wave packet will travel inside the medium. So this gave rise to first quantum revolution, which started in the early 50s. And the first device to be made from this concept was the transistor. Basically, transistor was a modern developed triode wall. So this was the size of a transistor. This is the size, and what a transistor you see is today is only 2 mm. It's on a fingertip. The second was the invention of the laser in 1956 by Manman and co-workers. And the biggest application of the laser is the fiber optical communication with the principle of total internal reflection. And the MRI scans and the PET scans that we are doing for our medical examinations are also based on the quantum technology. It's a quantum resonance there. And as far as the medical applications of lasers are concerned, ophthalmologists were the pioneers in using lasers. They are using lasers for keratectomy and also for the photocoagulation of the tissues. Then came the solar energy concept, and the principle of the solar cell is also the photoelectric effect. Then gradually we shifted to the second quantum revolution. In the first quantum revolution, we understood the quantum mechanics and we developed the technology based on the atomic concept. But in the second quantum revolution, we went inside the atom. We went to exploit the atomic scale. In the first quantum revolution, we just utilized the atomic concepts. We were not inside the atomic scale, we were not engineering with the atomic scales. But in the second quantum revolution, which is just in the turning into the third one, we went inside the atom. And the core principles are in the quantum superposition. Like my previous speaker said, that we are in qubits, we are able to have the two, 0 and 1, two states simultaneously. Physically, it's a spin up electron and a spin down electron. We have the probability through the Heisenberg uncertainty principle that both the spin up and spin down will exist together. So this is the basic principles of the quantum computers. So there is a quantum superposition, what we talk in physics. The second concept is the quantum entanglement. Like a particle can exist at two places at the same time, and the places will be at different places. And when you stop one place, the other will also be stopped. As far as we are mostly from India, you can get a concept from Indian philosophy about this. The third concept is the quantum measurement and control. This is like the Schrodinger I talked, gave a Schrodinger equation describing the motion of a wave packet. That is a particle, how any particle, be an electron or any particle, will move inside the atomic field. So, in order to exploit the quantum technology, we need to control this movement. This can be done by through applying the magnetic field, and magnetic field is the best example to exploit this. So the technologies developed with this concept are the quantum computing, but the quantum computing that we are presently using, is it really quantum? Or we are making it quantum through softwares? The hardware is not quantum, the hardware is the classical one, but we are using the software to go at this scale. And we are waiting that one day it will come that the whole device will be quantum. And the second is the quantum communication, which is based on the principle of quantum entanglement. Next is quantum cryptography, that is the encoding of data, be it in the DNA or any other form we can have. And the most advanced form is the quantum sensing, which is being used in metrology. And the application of the second quantum revolutions are AI and the machine learning, drug discoveries, financial modeling. We have talked about the first two, and the third is the financial modeling. We can use the quantum technologies in modeling, forms of financial modeling also. Like if you are doing an MBA, you also need quantum technology to develop the concepts. Climate prediction, national security, and the security I will come later on. How you will say, how will quantum technology be helpful in defense? Because you are using it for programming purposes. There is a quantum layer called graphene. You have heard of graphene? That's a single layer, and that is used to shield the fields. If you are having a radiation attack, you can shield your device or your building with the help of a graphene layer. Now we are into third quantum revolution. Like I said earlier, in the first quantum revolution, we used the atomic concepts. In the second, we manipulated the quantum concepts. And in the third quantum revolution, we are integrating the quantum concepts with AI. Now what we have started doing this. Like you use AI to govern your programs. If you use an AI to govern your qubit, any quantum program, quantum algorithm, then this is an emerging field, and this will go in the third quantum revolution. And what will evolve of it is quantum artificial intelligence. Basically, this is a combination of an AI generated quantum field. This is a field which has, like one of my earlier speakers pointed, that stability is still to come. Because in quantum, the entire concept is based on the probability. So, the maximum probability is 1 of finding the particle in a certain location. That is called the wave function. But we can't have the exact probability every time. Next we will come to quantum biology. This is the field, like sir was talking about DNA. This is the quantum biology, it is also evolving. Quantum materials, these are the graphene and other materials which are being developed are under this category, and this is also governed through the control, the deposition of graphene is controlled through artificial intelligence, because it's a single layer, single particle thickness. The quantum sensors and the Internet of Things, and how this quantum sensors work. If light is absorbed, it will eject an electron, and the conduction will be through the electron only. The quantum physics is only limited to the absorption part. What are the challenges? The first challenge is the scalability. Whether it will be possible to maintain the scales of microns practically. Like I talked about earlier, there was a concept of superconductivity came, but it was not feasible at the room temperature. Next came the concept of nanotechnology. 10 years back, we were hearing of nanotechnology. Ultimately, it was people were saying that why the effects are appearing at nanoscale. Then somebody discovered that it is nothing new, but it is a quantum concept only. Then this intersection of the AI with the computational fields will need physicists also, computer science engineers also, and the AI experts. So a collaboration is required to deliver it to the masses. And what we expect is the super intelligent computing. I am working on plasma. A plasma is the fourth state of matter, but for a physicist it is the first state of matter. After the Big Bang, what happened? There was an explosion, and whatever explosion it is, there is a rise in temperature, and at millions of degrees of centigrade, do we expect solid, liquid and gas to exist? At that temperature, only the plasma state was there. So plasma was the first state to come into existence after the Big Bang. And it will be the last state whenever the universe will get discovered. And it's 99% of the universe is made of this state. There are different regimes, low density regimes and the high density regime. The high density regime is at low temperature, and earlier it was thought that it's too cool and dense for the classical plasmas to exist. People were not studying this kind of plasma, but now these are the industrial applications of plasma. But now we are into this regime. These kind of high density quantum plasmas are found in Jupiter, white dwarfs and neutron stars, and core of the giant planets. And in the industry, all the semiconductors have this quantum plasma. In the magnetic fusion, in the inertial confinement fusion, we have the high density plasmas. In the dust, we have high density plasmas. And we are working on the, as far as theory is concerned, There was quantum hydrodynamical model was first model to be used. We first started with the, but it was they were non-relativistic model. Now we are developing. My group is developing quantum electrodynamic model, a fully relativistic model that will explain the electrodynamics of the quantum processes. And as far as quantum technology is concerned, for the electronics people, on the surface of a semiconductor, we have high density plasma. When a laser hits the surface of a semiconductor, the plasma is generated and a soliton wave is formed. We have analyzed the soliton wave, we have created the soliton wave, and we are going to achieve particle acceleration from this soliton wave. These are the challenges. And the quantum technologies have a metaphysical aspect also. Like we talked about two states existing simultaneously, it is a metaphysical concept. I will not go into detail due to paucity of time. And I've already published a paper on this tapestry of the quantum physics, bioscientism and Indian philosophy about this metaphysical concept. And as far as this talk is concerned, there is an article on the century of quantum revolution which has been published in Scientific India. So again, thank you.
I thank you, Dr. Kumar. This is really cool. I'm a computer engineering background, so I'm the physicist is one of you. So I have so many questions. So first, we would like to appreciate Dr. Kumar with a token of appreciation for this wonderful talk and keep us thinking. We would like to take a couple of questions. Ready, want to try? You good opportunity. Otherwise, I'm going to give a test. What is entanglement, right?
Thank you, sir, for your talk. I'm interested in the role of quantum physics in Indian philosophy, as you just mentioned, because I understand the metaphysics, how you define some kind of Indian sciences in which we believe, but as far as the philosophy, what philosophy you want to relate with it, and how quantum physics works in the Indian philosophy, that I'm curious to know.
Basically, it's a very to be discussed at length, but I will give you some instances. Like in the philosophy, you say that the same person can exist at two places at the same time. In Indian ethics, you will find examples. Same is the case with the quantum probability concept. You can have the two particle states at the same time, and that is the principle of the quantum physics. And we have many examples for this. This is a simple example that I gave you, and we can discuss it at length.
Another question?
There's one, since we are in Mathura, one very good example. Like when Draupadi called it, he was not present there, but he came. So it was quantum teleportation. He didn't came through any means of transport, he was quantum teleported to that place.
Can you say is another way of saying that is already that
First of all, thank you so much, sir, for
Philosophically
this.
it was there, and the modern concept came. We can relate the two through the bioscientific theory by Robert Lanza.
First of all, thank you so much, sir. Myself, Shabha. My question is, how does quantum computing play a vital role in encryption technologies in cybersecurity field using QND?
Basically, encryption is a transference of data through the spin states of the electron. it involves both the programming part as well as the physics part. I am not a technologist to go into details of it. You can have a person who is preparing quantum algorithms. He will be more suitable to give you how but the basic physics is that you can have the electron spin states manipulated and stored for the encryption part. But it is not done through physical means, it is done through quantum algorithm manipulation. And the programming person will be there to assist you for it.
Thank you. You can watch some shows algorithm. I think you will have fun. Thank you so much. Our next speaker is online. So we're going to try to welcome Dr. Manish Modani of NVIDIA, Pune, India. And he's going to talk about introduction to accelerated quantum computing. I think it's Q.Q, right? Or Q.Q, right? All right, so let's first welcome with okay. Okay, there's a flower over here. I don't think you can see it, but we're going to try to make sure put the picture like this.
Hi, am I audible?
Thank you. Enjoy.
Hello, am I audible?
Yes.
Great. May I start?
Yes.
Okay. Is my slides visible?
Yes, they are. We can see them. Thank you.
Great, great. So first of all, my apology not being there due to some emergency. I could not be there in person. Thanks for the invite to the organizers, and thanks for giving me chance to talk about accelerated computing and quantum technology. Before I start, if you see the right side, there is just some scan bar is there. If one scan here, then they will get the chance to register to the NVIDIA GTC conference, which is annual conference. It happens in US, St. John, so one can click on this and register. It's a free. They get all the virtual sessions recorded as well as live. They get chance to hear. And this is NVIDIA's conference. You will find what is happening latest in the world, including in quantum technology, AI, Gen AI, whatever is happening. All sessions will be there. It is in March, so it's a good to register. Right? So with that, I would like to start. Brief about myself. I awarded PhD degree in 2007 in applied mathematics. Then 10 years I worked in IBM, where I was at 3 years in IBM research in UK. In my last assignment in IBM, I was the country lead for the weather channel. It is same what you get the weather first when you search weather in Google, any weather information, first it comes from weather.com. So IBM acquired that time that company, and I was the country lead for that. And then after that, last 4 years, I am working in NVIDIA. My key roles are to take care of the key missions in NVIDIA, including quantum, National Quantum Mission, as well as now the latest AI mission is going on, that one, National Supercomputing and National Monsoon Mission. So I am the technical lead for all those missions. I work with all the academias, research labs, defense, with all I work and enable them with the accelerated computing. So let's start with today's thing, and just wanted to, before we start, just wanted to show one application where the fusion of high performance computing and AI, it helped in our day-to-day life. Because during COVID time, finding the vaccination, we all know it came
quicker than generally it takes around 8 to 10 years, but we got the vaccination in a couple of years only. And that happens because we have now accelerated computing, which accelerated the thing, and it was a fusion of HPC, high performance computing, and AI. Right side, what we are showing is the NAND code, which is the most popular molecular dynamics code, and it was running for Rhizome. And when we run only on HPC architecture, CPU-enabled HPC architecture, then we were getting the performance around 10 raised to power 7. When we made it GPU single node, we got performance around 10 raised to power 9 atom nanosecond. And then when we made it to multi-node, multi-GPU, we could reach up to 10 raised to power 12 only. But then the fusion came with AI and HPC work together. There are frameworks like DeepMD and so on, which works for molecular dynamics. They augment the HPC, and then what we got the performance with one simulation is 10 raised to power 8. So it's a multi-fold performance improvement when there is a fusion of HPC and AI, and it is happening. One way due to accelerated computing, we are getting the quicker results, and that is helping in our day-to-day life, right? In every segment, this is happening. So with that, would like to, before going to quantum, would like to introduce what NVIDIA is doing, why we are here today, where we are, right? So NVIDIA is ideally a graphics company which has started in 1993 as a graphics card, where the games come on these graphics cards. So for so many years we were known as a gaming company. Still we dominate that market as well. So we are known for, many people know for NVIDIA as a gaming company, right? In 2005-06 we came up with a layer called CUDA, and where one can exploit the number crunching on this graphics card, and that enabled to use this system NVIDIA GPU to be used for scientific computing. And then after 2012, we started AI journey, and then Gen AI, deep learning, and so on. So now coming back to this, we manufacture the GPUs. Now we do manufacture the CPUs also, ARM-based CPU. Now we are coming up with that. And then DPU is data processing unit. We acquired the Mellanox, so we have our own network as well. Based on that, the second layer goes, we have various kind of system based on that. I am sure everyone here, they might be using one kind of system here or there in their day-to-day research. RTX, TGX is our proprietary, HGX is our manufactured with our partner, the GPUs, then EGX is for edge computing, and so on, right? But then developer, they don't want to bother on this layer because the underneath architecture could be anything. So our CUDA layer works across all the architecture. If you are programming on one system, easily you can run on another system. The performance may vary, but at least the code is portable across all kind of GPUs. That's the beauty of CUDA layer. After that, we have many accelerated libraries like QNumeric for our day-to-day numerical simulation. Then QQuantum for quantum computation, which I will talk about. Then after that, we have various frameworks ready where one can come and write their application. These are being used across the domain, be it Gen AI, be it say Maxim is for live interaction in the meetings. You want to translate your language, that is the Maxim framework. Riva is for our language translation. Nemo is our framework where nowadays the LLMs and all, they are deployed, they are built, the foundation models are being built, they use the Nemo framework. Similarly, we have co-op and various other frameworks. The message here is, any kind of GPU you have, you can work across all these frameworks. Developers can start write their code. They are compatible across all the GPUs and across generation of the GPU. So developer no need to bother about underneath architecture. If someone is doing research in these architecture, then they can also go deeper into that. But as a developer, many users are they work on application layer, so they no need to bother underneath architecture. That can work across the seamlessly across all kind of architecture based on NVIDIA GPU. So based on that, now let's come towards the quantum computing, where it is and where we are heading. Right? So if you see the historically, first the architecture comes, and then people start working on that, and then we had new innovations based on that, right? So initially there was, say, GPU-enabled system available, then CUDA came, it started using for scientific computing. Then those systems were available, and then we see the innovation with the deep learning and now generative AI, that segment is going on. And for quantum computing also, now the stage where we have various kind of architecture available. In terms of quantum computer, there is a race going on, the superconducting ion trap and many kind of quantum computer. People are ready with that, and development is going on. Day by day, we are rapidly seeing some innovations are coming up. We are trying to reach there, right? So, but still, as a developer, sometimes developer get nervous that if I am writing the code for one kind of quantum computers in superconducting, will it work on ion trap and vice versa? Or there are other kind of quantum computer coming and so on. So that is sometimes they get nervous. So that answer also NVIDIA has now to make people quantum ready. We have our framework ready, easily accessible. Now one can do simulations on our available system. I will talk about it. But the message here in the slide is right now is the time to work on quantum computing domain. The system availability is there. I will talk on that. Be ready for quantum computing. This is going to be reality in near future. So how it will work? Quantum computer. The thing is, the quantum computer will work as an accelerator, like I shown my first slide, where GPU and CPU work together to solve the COVID problem. Same way, quantum computer will also work as an accelerator. Any supercomputer you take, there could be GPU as an CPU is the main part. Then there could be GPU is one kind of accelerator. Then FPGA could be another kind of accelerator. Same way, the quantum will be one kind of accelerator with our supercomputer, right? And what will happen is, the pre-processing will always remain on CPU. Then co-processing, where we have quantum algorithm and all, they will be offloaded on quantum. Again, post-processing, again it will come on CPU. Now, the quantum part will be taken care by quantum. The CPU part may be taken care by CPU or maybe GPU or FPGA, that is separate thing. But what I mean to say is that it will work as an accelerator, dedicated accelerator for certain kind of computation. So application will start on CPU, part of it will go on QPU, and rest will remain on CPU. So that is understanding. All researchers are saying that future hybrid, any application will work on both CPU and GPU. Right? Now for developer, the question comes is how they should write the program, because one side quantum computer keep on evolving, that is one. The another side is how it will interact with the classical computer. Classical, I mean CPU or GPU enabled system called classical and quantum. How they will interact, how quickly they will interact, because as I think my previous talk, the discussion was the challenges around quantum computers. So how long the qubit will retain its position, or how long the coherency will be there. So time to solution has to be fast, their communication has to be fast, and how they will communicate. One side is a bit, one side is a qubit, like in layman language we can talk. So how that will talk. For this in 2020, Microsoft came up with the standards. There is a consortium has been made. In 2020, Microsoft came with the standards, and there they gave the protocol how classical and quantum should integrate. Right? This problem is already solved. Right? To address that, NVIDIA came up with all solution in terms of hardware, in terms of software framework. First slide I would like to show as a hardware solution. There we have our base CPU and NVIDIA GPU together. Now they have one more connection, PCI connection, which talk to, if they get integrated the classical computer and quantum computer. We have DGX quantum, where we have extra connection which goes and talk to quantum computer. And that's where we are saying our latency DGX quantum, if you see the bottom side right, we are saying that will be around 400 nanoseconds, the latency. And that is the acceptable limit. So NVIDIA hardware is compatible with quantum computer, they can interact fast, and that will give the edge for the computing that okay, in certain time we should perform our computation and that will give the desired. So hardware side we have this DGX Quantum. We work with all the partners. So one thing let me admit again, NVIDIA is not building any quantum. We are enabling the quantum computing, we are accelerating the quantum computing. I will show the meaning of acceleration, but we are not building any quantum computer, we are providing the platform. And this, whatever I am going to talk today, any kind of GPU enabled system you have, you can run there. There is no need to go for any specific GPUs, any specific stuff. One can start work even as soon as their RTX maybe card will be available on your laptop. You can start from there, or there is any server there anywhere you can start. Right? And how it is possible, I will talk about in subsequent slide. But we are making everyone user to be quantum ready so that they can start writing their code, understand the code. Right now it's in simulation mode, but tomorrow whenever you have actual quantum computer access, you can run the same code there. And to do that, NVIDIA is partnering with all the ecosystem, be it simulation frameworks, system builders, software, research centers, cloud service providers. Like we are partnering with all the quantum service providers. In this list, day by day.
I only have 5 minutes.
Okay, I have only 5 minutes. Okay, I will try to. So what we have is, we have the CUDA queue is the layer. If you see this CUDA queue, that is available as a container. What it does is, you can download this container. What it does is, it accelerates your, it allows you to write your code in terms of CUDA, quantum language, that will run tomorrow. Today it will run on classical as a simulation, but tomorrow part of the code can be offloaded on quantum without any issue. So that will help you to classical quantum integration. As well as you can start working on AI for quantum, where you can use AI techniques for quantum error correction, calibrations and algorithms. Right? Again, this is a container freely available. You can download on any kind of GPUs, and it supports C++ and Python language. It has its own compiler, we call it MBQ, and then it supports all kind of applications. Right? It is interoperable, which does all, it supports all OpenMP, NPI and CUDA languages. How it works? So if you write any code, suppose that part of the code should go on quantum, so you simply, there is a flag code queue, spin, those will go on quantum. The bottom side is a linear algebra factorization, which will work on GPU better. So here, you will just simply call the GPU enabled libraries. And compiler, it takes care, okay, if it is a production, it will do the simulation if we are doing only on classical, but whenever quantum will come, it will offload. And how it works, the code is written once. Now at compile time, you just need to change the flag. So the bottom line, I am giving the name of the quantum computer, Quantum, hence the application run on quantum. Above side, I gave the quantum, which means it is simulation, it will run on classical. So any developer can develop their program in CUDA quantum, and then from there they can take it forward. The application written today, tomorrow it will run on any kind of quantum computer. Hence we are making people quantum. Would like to show quickly few results now. So these are the results run on this CDAC Arawa system, which is the 75th number on the globe top 500 system. Here the common algorithm like Shor, UFT and Sycamore. The GPU allows to run for larger qubits, like I am showing the results for 30 qubit, 32 qubit of UFT. And when we run on GPU enabled simulations, in comparison to CPU, they are more than 100 times faster. And this were published long back in many research papers. Similarly, would like to show one more paper, and then I would like to close. So this is the VQE algorithm, the 2D Ising model. It's a variational quantum algorithm where what we do, part of the algorithm run on CPU, part of it run on quantum processor. CPU here we initialize the circuit, we parameterize, and then main processing goes on quantum. Again it comes back, the iteration goes on. Right? So for to solve this is the circuit I made. It is around 36 qubit I made the run. So I am showing how the circuit looks like, how these are entangled, all the qubits. And then this is the performance I get. It's similar code for simulation if I run. And here I use the framework which is from Google. And similar code if I run on CPU, how long it will take. And if I run on GPU, A100 CPU, how long it takes. If you notice, I could run with the 34 qubit. Here on CPU it takes 1600 seconds, whereas on GPU it took only around 1 second. That was the speed of what we get. This is recently we published in the ISC International Supercomputing with EIFR. We published this as a poster there. This is the HHL algorithm which is commonly used in quantum. Again, that simulation got accelerated and we got a speed of around 8 times or more than that for 16 qubits. And this was be shown even for 25 qubits, the speed of was much more. So with that, I would like to end and happy to have questions. Again, the scanner is there. If anyone would like to register for GTC, the one can get all the talks and other access to the talks and recordings. Thanks a lot.
Thank you so much. It's Q Quantum. This is really cool. NVIDIA is hot. Okay, so
Thank you. The weather is also hot.
think about the energy also hot. We would like to take a couple of questions, but before that, we would like to present a token of appreciation again remotely.
Thank you. Much appreciated. I am privileged to be here and got chance to present. Thanks to the organizers.
Hi, can I have a question or is there a queue? Hi, can you hear me? Or
I can hear you, but
okay. I can I ask a question or?
unsure how moderator speaks.
Yeah. Oh, wait.
Oh, like this. Okay. Got it. Okay.
Okay, go ahead and ask question.
Oh, thank you. Very kind. A quick comment to Dr. Manali's point. I personally work with quantum libraries for a bit now, and people tell me doing the same. So, number one. Okay, I just had a quick question about your HHL work that you're doing. Obviously, you're using from the NVIDIA side, you're using some numbers, right?
Yes. Yeah, for simulation. Yeah.
Exactly. So, have you made any comparison on the matrix? HHL is basically matrix inversion.
Right.
So,
Right.
have you made any comparison in matrix conversion performance between what you're getting and, for example, what IBM has or Rigetti has, which is
Oh, okay. So for simulation wise, there is no comparison required because even we can work on IBM Qiskit framework and make it faster on our GPUs. So our quantum library that makes faster the Qiskit, Penguin, SIR, all the framework. So one way the quantum enables all the framework like in AI, we go TensorFlow, PyTorch, all these are faster on GPU. The other side we came up with CUDA quantum, that is our framework, you can say kind of Qiskit or Penguin. But our CUDA quantum framework is easily integrable with all kind of quantum computing, with ion driver power. So that's the difference. But accuracy wise, they are not a problem. And we can do faster. Yeah, that's where one simulation I shown with the circ, what faster we are getting. So I wrote the code in circ and then we showed the simulation. So we are open with that framework.
Yeah, I'm familiar with the SARC thing. I'm doing very similar stuff for image analysis. And yes, I agree. I mean, your Lightning.GPU for Centennial is quite efficient actually. It speeds up about for Apple chips. Yeah, thanks a lot. Great talk. Happy to have been here. Thank you.
Thank you, awesome. We have one final question. Anybody want to try? Okay, I guess I can try. Okay, so what about like optimization? I think there's a Q optimization, right? But there's not quantum, right?
Sorry, optimization means?
Okay, so like you have digital annealing, you have genetic algorithm. So I think I remember there's a Q optimization. Q dot optimization, is that one?
No, co-opt. That is
okay, co-opt.
Talking
Okay.
about co-opt.
Yeah.
That is the framework which does the optimize the movement when you go.
Oh, okay.
That is nothing to do with quantum.
Okay.
If you are finding the optimal path and
Okay.
other thing, then there is a co-opt is a library what we use for
Okay.
finding the optimal path.
Okay.
Be it in by even chip designing time, that also being used, as well as in the factory layout, we use that, how the robot should move and so on. So
Okay.
there are various use cases. But before I close, I would like to give one thing which I do not have readily link available, but for any faculty who would like to start the course on quantum, NVIDIA supports that. We have CUDA Q Academic. Just search this Google, or otherwise please connect with me. There we have various all kind of quantum algorithms, including QFT, Shor, basic algorithm, kernel, everything is available. Programs are available, modules are available. One can take that, make part of your coursework, give the hands-on. We are happy to support, happy to partner. Anyone can come forward and we can take it forward. So many things are readily available, no need to reinvent the wheel. It will help in day-to-day classwork.
Awesome, I really appreciate it because I have a class in quantum computing, so I think I'll be
Yes,
your
please.
first customer. Okay.
Most welcome.
Oh, thank you very much. We started with this most amazing first session. It was 30 minutes behind, but now we're almost catching up. So please come back at 2 o'clock for the last 2 talks. And then tomorrow we have 3 more talks. Thank you so much.
Happy lunch. Thank you. Bye-bye.
Thank you so much, Professor Shi, for heading this wonderful talk session. We will continue after the lunch.
हाँ